Hi. So today I'm going to talk about incremental view maintenance algorithms. In the last lecture, we had mentioned about view maintenance in general, right, and the different kinds of techniques that are there for maintaining views, maintaining materialized views. So, and we discussed that it is not always possible to drop the view and create it again based on the changes that are happening at the happening in the underlying base tables from which these views have been drawn. So it becomes critically important that we maintain the views in an incremental way, right? So today we are going to look at some of the techniques for doing so. So incremental view maintenance. So the motivation. We all understand that motivation now, right? And then we'll be looking at how joins and different many other operators in relational algebra can be handled in an incremental way. And the prerequisite for this is relational algebra. So you should be conversant with relational algebra, and I'm sure all of you are conversant with RA. And material for this particular lecture has been taken from chapter 13 of the Silberschatz book on database system concepts, 6th edition of that book. So view maintenance. So let me begin. So view maintenance. So the changes which are either in the forms of inserts or deletes to a relation or expressions are referred to as its differential, right? And let us say the set of tuples to be inserted or deleted from a particular relation are IR and DR respectively. That means IR is the set of tuples I'm inserting into R, and DR is the set of tuples that I'm deleting from R. And as I said, we'll be focusing only on inserts and deletes, because updates can always be thought of as deletion followed by an insertion. So you delete the old tuple and insert the new tuple with the updates. So how to compute the change of the result of each relational operation given changes to its inputs? So that's what we are trying to discuss. So if we are able to discuss this, then views are nothing but a collection of operators, so we will be able to handle the views also. So let me begin this with a very not simple, but with an example of an operator which we use extensively in data warehousing, and that is the join operation. So you need to join the dimension tables with the fact tables for every query that you execute on a data warehouse. So let me say that you have a view V, which is a join of two relations R and S, and there's an update on R, right? So let me put this update in the form of delete or an insert on R. So let IR be the set of tuples be inserted in R, and DR be the set of tuples deleted from R. So first I'll talk about inserts. So for that I'm introducing some notations. So R old is the old relation R, the original relation R, and R new is the new relation that you obtain from R after inserting IR into R old. So R old is actually, R new is actually, so if I write it here, R new is nothing but R old union IR. So this is how I define R new, right? So consider the case of an insert to R. So that's what I'm saying. So R new join S. So what we need to, so V new, I'll work out something for you here so that it becomes easier. So V new is nothing but R new join S. Now R new, as you know, is nothing but R old union IR join S. That's what is mentioned here. So now I can use the rules of distributivity of union over join, and rewrite this as R old join S union IR join S, right? And this R old join S is nothing but V old. Okay, so this V old is actually V old, I'll write here again, is equal to R old join S. So this is V old union IR join S. So this is what we are writing. So you can see here that I can compute V new using V old. So I'm using V old as it is, and plus I just need to do this kind of operation. And since IR is, the number of tuples in IR would be much smaller than R, right? So this join with S would also be small, right? So V old union IR join S is equal to V new. So the new view is computed in this fashion, and this you can see is much cheaper than doing something like this, R new join S. That means I insert some records into R, come up with R new, and then join it with S to come with V new. So this V new here that I've written on top is much more expensive than the V new that we have defined here in this box at the bottom, right? So we save a lot of computation time, or a lot of computations by doing this. So this is how we carry out the join operation in terms of inserts on one of the relations. Similarly, inserts on S can also be handled in a similar fashion, and I'm using V old as it is, right? And what is the extent of change in this? Extent of change is IR. So you can see the cost is proportional to IR in the sense that I have to just compute IR join S. So the cost of updating the VO is proportional to the extent of change, or the amount of change. So that's why this way of doing it is incremental, is doing it in an incremental fashion, right? And similarly for deletes, so V new would be V old minus, so all of you know the minus operation, so V old minus DR join S. So again it is proportional to DR. So this is how we can handle V new in when there are updates to R or S or to both, right? So I have here taken up only one case, that is I am inserting some records in R and deleting some records in R from R, right? So similarly you can talk about other cases using the same kind of concepts. So this is how I handle the join operation. So let me now come to the next, so let me clear this annotation. So now I'm doing it on selections and projections. So selection, so suppose you have a view which is a selection on R, and there is some condition theta that is to be checked for selection. So V new would be equal to V old union sigma theta IR, and V new in case of deletions would be V old minus sigma theta dr. So it is very simple that you are adding some tuples IR, and you apply the condition, the selection condition on IR, and whatever records qualify for this have to be appended to the old result that you have, that is V old. So it is very simple. Similarly, if I am deleting certain records from R, right, dr, so I apply the condition on this and then subtract it from the original result. So whatever tuples qualified for the result or contributed to the result from dr have to be removed from the result. Similarly, now let me talk about projection, which is slightly more involved than selection. So suppose you have R is equal to AB. So this is a relation which is two attributes, and let me take an instance of R which is represented by small r, which has two tuples in it, A2 and A3. A is the value for the attribute A, and 2 is the value for attribute 3, and similarly the next tuple that you have. Now pi a r, if I do, that is a projection of r, if I do on A, I get a single tuple A, right? So if we delete the tuple A2 from R, we should not delete the tuple A from pi AR, right? But if we delete A3 as well, right, we should delete the tuple A from R, pi AR. So you have A2 and A3. So if I delete this, I should not be deleting A from the result, right? So what we need to do is we need to keep a count, right? So on insert, so for each tuple in projection pi AR, we need to keep a count of how many times it was derived. So if I look at A, so it was derived 2 times, so the count for A is 2. So if I delete one instance involving A, so this count, so suppose I delete A2, so this count becomes 1. So that doesn't mean that I would delete A from the result, because it still is there because of A3. Now if I delete A3 as well, then this count becomes 0, and then I would be deleting it from the result. Okay, so this is what I explained the delete part, right? Similarly on insert, so on insert of a tuple to R, if the result tuple is already there in the projection, we increment its count, else we add a new tuple with count is equal to 1. So we set the count is equal to 1 if it's a new tuple. So that's how I handle projection. So this is selection and projection. So let me now come to certain aggregate operators which we extensively use in data warehousing. So now first operation is count. So this is an extended algebra. So this is like on R, I am trying to do a count on B, and I am doing the grouping by attribute A, right? So when a set of tuples IR is inserted to R, so what happens to the count? So for each tuple T in IR, so I look at the set IR, which is a set of tuples which are inserted. If the group T dot A is present in V, we increment its count, right? Else we add a new tuple T dot A comma 1 with count is equal to 1. So this indicates the count, right? So this is how we do it. And when a set of tuples dr is deleted, so we first look in the group T dot A and subtract 1 for the count for the group. And if the count becomes 0, we delete from V the tuple for the group T dot A. So it is more or less similar to projection. So here you understand that when I insert some tuples, I would increment its count, and if I delete, I decrement, and if the count becomes 0, so that particular group is deleted, okay, from the metallized view. So this is what is count. Now the next operator is sum, which is again much more is slightly more involved than count, and this is an example that I have put. So you can add some tuples here, right? So this is my R, right, and this is my metallized view. So I can add some tuples here and or delete some tuple from here, okay, and then work out based on the previous slide, work out the results which are given here. Okay, so this is basically for sum, so which I am going to discuss next, but I can also have a count here. So instead of balance, I can say there are some counts here, say 30, 40, whatever, right? So you can apply it there. So here is the sum now. So sum more complicated than count. Now we have a metallized view which is like sum B over A, that is group by A on R. So maintain the sum in a manner similar to count, except that we add and subtract the B value, not the count, right? Okay, so we add and subtract the B value instead of adding or subtracting 1 for the count. Additionally, right, maintain the count in order to detect groups with no tuples. Such groups are deleted from V, and so we we cannot just rely on sum being 0. So sum being 0, still sum may be 0 despite the fact that there may be some tuples in that group, because they all are contributing 0 towards that the sum, right? So just we cannot look at the sum and remove that group from the view. So actual sum may be 0, but there are tuples in the group. So that's why we need to maintain the count as well in order to delete that particular group from the view. And to handle the case of average, so average is nothing but the sum divided by the count. So you have to maintain sum and count separately, and then at the end you do the divide to get the average. And similarly you have min, max, right? So if you have understood how we handle these things, then it becomes straightforward to work on any other aggregate operator. But just for the sake of completeness, I have included this min, max, right? So say here the example is for min, right? So A, G, min, B, R. So that means minimum of B grouped by A on the relation R. So handling insertions is straightforward. So when I insert a value, say suppose I have a min of say 20. Now I'm inserting a value which has a value of 25. So suppose I am doing min. So I just need to compare it with the current min, right? So if it is more than current min, I do not do anything, right? But suppose this value was 18. So now I have to set the new minimum as 18 instead of 20. So that's what, right? So maintaining the aggregate values min and max on deletions may be more expensive. So handling insertions is simple. Similarly for max, so suppose my max was 30 and the new tuple that comes in is say 25. So I don't do anything. My current value is 30, but I insert a value of 50, so I have to update this. So insertions are simple. Now need to look at other tuples of R that are in the same group to find the new minimum when the tuple corresponding to the minimum value of the group is deleted. Now suppose the minimum was 20, right? And there are other values which were like 21, 22, 23, right, 29, 30 and so on, right? So if I suppose delete the minimum value, then I have to look at all the other values to find out the minimum, right? So same thing with maximum. If I delete the maximum, right, so I have to find the next maximum, right, the maximum from the remaining tuples. So insertions are simple and deletions are slightly more involved, right, as compared to insertion. So this is the min max example. So what I've done is I have given you some idea about how to handle different operators of relational algebra, right, individually. Like I've looked at join, I've looked at selection, I've looked at projection, I've looked at count, sum, min, max, right? Now you know how to handle these independently, right? Okay, so if there's a min in a view, so I know how to handle it. If there's a max in the view, I know how to handle it. So now when we come up with expressions involving these operators, so those can also be handled in a similar way, right? So I'll now close this with an example, so which is like the minimum marks in a test for student records, from student records. So you can find out. So I'm trying to find out the minimum marks for test 1 and test 2, right? Although I can add another tuple here, T3 with 10, right? Because T3 is another component, right? So now if I insert a record, say for example here, if I insert a record, say T1 A 100 with marks minimum, I'm saying, right? So if I'm saying insert marks with 10, so what will happen is that I will compare it with the current minimum, which is 15, and I'll update it to 10. Similarly, if I insert a record T3 A 500 and minimum marks are set 10, so if I enter 5, so I'll have to change it to 5 for T3. So like this, I can handle inserts and deletes to a relation R. In this case, it is this, right? And incrementally handle these updates. So with this, I close this section on incremental view maintenance. So view metallization. So with this, we try to conclude this section on view metallization. So I'm just trying to summarize what all we discussed. So view metallization per se we discussed, like what is the concept motivation behind this. Then we talked about selection of views to metallize, which is an NP complete problem, right? And there are some models or methods or algorithms using which you can select views to metallize, and most of these algorithms are heuristic in nature because it's an NP complete problem. Then view maintenance, we looked at why we need to maintain views and how we can do that, when, how, those questions we answered. And then today we discussed incremental view maintenance, where I looked at all the operators, most of the operators in relational algebra, and once we know how to handle them incrementally, we can handle any relational algebra expression incrementally. And metallized view is nothing but a relational algebra expression, right? So with this, I wind up this section on metallized views, and the next section, or the next technique that we need to discuss in this module number 7 is bitmap indexes. So the next lecture will be on bitmap indexes. Thank you.